somehow supposed to extrapolate this as though eukaryotic organisms somehow evolved from prokaryotic organisms. So it's just assumed there, brought up in the freshman textbook. What Behe and many others are saying now is that's no longer adequate in science today. You're going to have to do better than that. Whenever we look at the structure of a cilia, you're going to have to explain how you put this 9+2 thing arrangement together in a Darwinian mechanism. And no such mechanism exists. Furthermore, no such mechanism has even been proposed. And every experiment used to try to make the cilia, even in, whether it's in a prokaryotic or eukaryotic cell, try to make a cilia that works without being in its fully constructed form, has failed. So how in the world are you going in a natural selection process going to build one of these things from simpler structures? No model explains that. The only thing that can explain this are the kinds of things that make scientists very uncomfortable. And that is that somebody must have put the first one together. There was a designer somehow of living things that put a structure like this together from the get-go. The Darwinian mechanism has nothing to help us build this, but it has to be explained. Now, in his second book called The Edge of Evolution, Behe goes on to explain the mechanism, the construction tools within the cell that are used to build these things. And as it turns out, those construction pieces are also made of proteins. And building them using natural selection processes is even a worse problem than building this one. So the problem appears to be getting worse and worse for explaining the structure of things based on the Darwinian model, in my opinion. Now, once again, to the cell membrane. I'm going to return to that in just a moment as we finish this section. We look at the cell here, and I've talked about the proteins inside the cell. Proteins describe the anatomy of the cell. Proteins that describe things sticking off of the cell. And now I want to talk about the proteins that we find in the cell membrane. Your textbook tells you that the cell membrane is a fluid mosaic model. And this is a picture, a mock picture of a cell membrane. And you guys know this from your 9th grade biology or before. My kids were taught it in the 3rd grade by Ms. Versalotti, Phoenix Magnet Elementary. You can see the cell membrane has these polar heads and non-polar tails. It is a phospholipid bilayer. There are cholesterol stabilizing features in here, and these things are constant. You can see some of the proteins within the cell that create some of the ultrastructure listed here, but the picture here is designed to teach students about the proteins that are actually in the membrane itself. So I've talked about cytoskeletal proteins in here that will help me identify the cell. I've talked about proteins that stick off of the cell. I have talked about proteins in the matrix outside of the cells. And now I'm talking about proteins within the cell membrane itself. Now, your textbook calls the cell membrane a fluid mosaic model. What is fluid? What is a mosaic? A mosaic is a piece of art, right? So if you were going to generate a mosaic, you would use bits and pieces of something to create something larger. So a mosaic is like you break up a bunch of colored glass, reds and blues and blacks and all that, and then you use the fragments of that glass in a frame to make a picture out of it. It's a mosaic. A fluid mosaic is a little better described by a kaleidoscope. So some of you guys are too young to know what that is. You look through a kaleidoscope and you twist it. The artwork that's in there changes every time you make a twist. That's a little bit closer to what we're saying when we say fluid mosaic. The anatomists think of the cell membrane as a piece of art. As it turns out, this art is fluid. It is ever-changing. And by that we mean that the proteins that are within this cell membrane are always moving around, creating an ever-changing piece of artwork. So the question becomes in this fluid mosaic model, what are those proteins there for? They certainly are a part of the anatomy. And so I have a couple of pictures here out of your opening chapter in your book to talk about this. The proteins that are there certainly have a lot of physiological significance. And I am going to beat this horse to death in physiology. If you want to make the body work, you got to have proteins in the cell membrane that let charged ions go through. So transport for charged ions, binding of hormones, cell signaling. The proteins in the cell membrane do a lot of really important things. Now, you'll recognize some of this already. In addition to having those very important functions there in the cell membrane for charged ions and for binding, they serve as receptors for all kinds of things. Those are physiology things. We know that these proteins also attach to the cytoskeletal matrix, the inside of the cell, and they attach to the extracellular matrix. So they're part of, their extensions are part of that glycocalyx on the outsides of the cells. Now when I get to connective tissue, I'm going to take that just one more step and talk to you about the structures of proteoglycans on the outsides of cells. We're going to hold on that for now. I just want you to see that wherever you go, you're describing the interactions of proteins with each other. Right now, we're in the cell membrane. Now, the last piece of this is to talk about these proteins and how they actually bind cells together. So we're going to do some more of this in connective tissues because the matrix of connective tissues have cell adhesion proteins that are a little bit different. So I'm going to show you those as well. But again, the story is going to be protein. But every opening chapter, in the opening chapters of every A&P book, is going to have a discussion about how proteins are used in creating junctions between cells. And these will be of continued importance for us. So I'm going to slow down a little bit here. So the first one here to talk about are the tight junctions. Tight junctions are actually protein molecules that zip cells together. Did you hear the way I said that? They zip them together. So this cell here is being unzipped. So you can imagine these little protein molecules here that are forming these tight junctions being like a zipper, then you'll remember this. So when you zip something up, you link it together. So as we begin our discussion of epithelial tissues, the first one we're going to look at are the simple squamous epithelial cells. That's going to be the first one. And I'm going to tell you where some of these are. The first example we're going to give is inside blood vessels. So all over your body, the inside linings of your blood vessels are flat cells that are linked together. And they are linked together in different places in different ways. In your brain, the flat cells that are inside your blood vessels are linked together by tight junctions. They are zipped together. So one of the first concepts you learn in brain anatomy is the concept of the blood-brain barrier. And students think, when they hear blood-brain barrier, they think, well, when I'm learning the anatomy of the brain, I see that it's got coverings around it. It has a layer of meninges covering it. So they think, well, that must be a barrier. That is not what you mean when you say the blood-brain barrier. When you say the blood-brain barrier, what you mean is this. The insides of the blood vessels are linked together by proteins. So if you're going to get something into the brain that you put in your mouth or in your blood system, you have to deal with this. The blood-brain barrier serves as a barrier. You have to get things out of circulation into the brain, they either have to be lipid-loving, they got to be able to get across the lipid layer, or they have to have transport mechanisms. Something has to carry them across. So this is a serious matter. You treat Parkinson's, you're going to give people dopamine for Parkinson's because that's a problem? That's not going to work because dopamine's a charged molecule. It's not going to cross the barrier. So you got to think of something else, another way to get it across this, the tight junctions that form the blood-brain barrier. Proteins, zipping cells together. Here's another one. These are desmosomes. The first place we're going to talk about desmosomes in any detail is in skin, because the cells of the stratum spinosum are held together like this. Now, this arrangement of holding them together is a little bit different than the tight junctions. So you can see over here these globular molecules on the insides and outsides, labeled plaques here, on the insides and outsides of a cell. So here's cell 1, here's cell 2. And you can see all these purple lines here linking it to cytoskeletal elements. All of this is protein. Connections and linker proteins that are used to hold all of this mass together. So this is made up of a couple different proteins. This one's made up of a couple different proteins. This one's made up of a couple different proteins. And then look, from this cell membrane to this cell membrane, there are linkages across the cell. Those are proteins. So I sometimes describe this as like the rivets on an aluminum boat. If you're familiar with the bottom of old aluminum boats, they make them all welded now, but in the old days, they put two sheets of aluminum together and drill a hole through it, and they put a nut with a head on it on this side that had a nut that attached to it with a head on this side, and there'd be a bar that went through the two. That's always where your boat leaked because they had a hole through it. We call them rivets on the bottom of an aluminum boat. As it turns out, the cells of the stratum spinosum in your skin are riveted together. It's one of the things that gives skin its particular nature. Part of the strength of the epidermis is the desmosomes that hold the cells together. So that's another strategy. You're going to see it in the integument system. Tight junctions and desmosomes. Here's another one. This one's a special kind of junction between cells that is also protein, and this one is called a gap junction. So once again, proteins are linking the cells together here. The anatomy is linking them together. But in this case, you recognize a protein name that I mentioned just a second ago. In this case, the gap junction is actually a hole, a non-specific hole that connects cell 1 to cell 2. So in places in your body where there are gap junctions, it means that whatever is in the cytoplasm of this cell has easy access to the cytoplasm of this cell. Or another way of saying it would be, whatever I do to cell 1, I'm probably going to do to cell 2. They effectively create a single cell. The gap junctions between them cause the cells to be united. They do the same thing together. So there are a lot of places where this is important. For example, when we look at heart muscle, coming up on Monday, if not Monday, we'll get to it Wednesday. It's going to be Monday or Wednesday by the time we get there, probably Wednesday. When we look at heart muscle, we're going to try to explain the differences in the anatomy of the heart muscle cell versus a typical skeletal muscle cell. The truth is, if you look at them in high magnification, you can't tell them apart because the striped appearance is in the skeletal muscle cell and in the heart muscle cell. They're both striated. In fact, functionally, the actin and myosin of these two cell types do exactly the same thing. So there have to be some clues when we look at it to be able to tell them apart anatomically. How do you know you're looking at heart muscle cell and not skeletal muscle cell? This is the easiest one. These things are not in the skeletal muscle. Gap junctions. We call them intercalated discs in the heart muscle. And so I'll point them out to you on Wednesday of next week when we get there. These intercalated discs are gap junctions between the cells. What that means is the entire muscle mass behaves as though it is one cell. Can you see the value of that? I don't want my skeletal muscles to work like that. I don't want all of the cells in my bicep to contract every time I use my bicep. That is not efficient. So I'm going to separate those guys out and use a motor unit system to do that. But when my heart beats, I want it working as a single unit. Every time they all contract, and then they all relax, and then they all contract. And the reason they're able to do that is because they're connected by proteins that are gap junctions. Now, let's finish this by a brief outline of how you make proteins, and then we'll begin our histology. Okay, so this is the primary structure of protein that you all are very familiar with.